Hey guys, and welcome back to the channel. So this was the NetBank Data and Analytics Masters Challenge, which is a national competition aimed at identifying and recruiting data professionals in South Africa. I actually competed in the data engineering track and finished third. So I want to walk you through how I achieved that. The whole pitch about the challenge was prove it on real banking data. It was a two-track challenge. We had data science and data engineering, and it was really geared toward senior practitioners. So if you are a student or starting out, this might feel a little bit stretched for now, but it's really a great benchmark for where the bar is set. So we worked with anonymized banking datasets that were built to feel like an enterprise complexity, not the toy datasets you'd see where everything is already set and clean and tidy for you. To make it to the finale, you needed to land in the top 50, that's top 25 from each track, and those finalists then had to go to on-site finale in Johannesburg with a total prize pool of 500,000 Rand. But honestly, the prize money here isn't the biggest draw because you could also land yourself a job. And to think about it, these guys, instead of sifting through thousands of CVs, they've got the best 50 data professionals in the country who actually engaged in the challenge sitting in one room. That's recruitment on easy mode, guys. Anyway, let me take you to the challenge brief. So once you are in, here's what the data engineering track actually throws at you. So the scenario here is the bank has partnered with a fintech to serve unbanked customers. The fintech runs the virtual accounts and the transactions, and then the bank holds the customer identity data, and your job is to stitch it all together. So you are building a medallion pipeline. You've got your bronze, silver, and gold across the three messy real-world sources: customer records, your account data, and about 1 million transaction events in the JSON files. So everything runs inside Docker with hard limits. So you've got 2 gig RAM, you've got 2 CPUs, and a 30-minute time limit. You have no internet access. So this isn't about writing code that works on your laptop, really. It's about writing code that survives production constraints. And you are also scored on 4 things. That's correctness, scalability, maintainability, and the efficiency. And your sloppy Spark code actually costs you points here. Okay, so let's look at the 3 files we actually had to build. So we've got the ingest, the transform, and the provision. So these map directly onto the bronze, silver, and the gold layers. So starting with the ingest.py, which is basically the bronze layer file. This one is relatively simple, guys. So the instructions are basically don't touch the data. You just have to read the 3 source files, the accounts, the transactions, and the customers, and then you write them out as is into Delta Lake tables. The only thing you add is the ingesting timestamp column, and importantly, that timestamp has to be consistent across the whole run, not generated per row. So you'd actually capture it once at the start and then stamp every record in that same value. A few things worth flagging here. First, everything is config driven. So your parts come from the pipeline config YAML file. Nothing is hard coded. And then the second thing is you run Spark local 2 mode because of the 2 vCPU constraint. And the third thing is the Delta paquet, not plain paquet. That distinction matters because Delta gives you transaction logs, schema enforcement, and the ability to upset later on, which becomes relevant in the silver layer. So bronze is really just lend the data, timestamp it, store it in a queryable format, no cleaning, no joins, no logic whatsoever. So it's your audit trail. If anything was to break downstream, you can always trace it back exactly when the data arrived and when. Now, transform.py is the bronze to silver. So this is where most of the actual engineering happens. So we've got 3 big jobs that we need to do in this stage. So the first one is deduplication on natural keys. So for accounts, we're going to deduplicate on account ID, transaction ID for transactions, and then custom ID for customers. Remember from the data dictionary, Stage 2 injects about 5% of the duplicates transactions with slightly different timestamps. So your dedupe logic needs to handle that, not just exact match duplicates. But this is for stage 1. So stage 1 has clean data, so we don't have to worry more about deduplication. And then the second one is standardization. So dates come in as strings with mixed formats. You've got your amounts also need to be casted into decimals, and the currency can also come in different variations. So we need to cater for that as well. And then the third one, which is part of the stage 2, is the data quality flagging. So I'm going to skip that for now because this is only going to come into play in the stage 2. But we're going to be talking about data quality implementation in stage 2. Finally, provision.py, which is the silver to gold. This is the dimensional modeling layer. We are building 3 tables. We've got the fact transactions, the dim accounts, and the dim customers in a classic star schema. So the first big requirement is the surrogate keys, right? So these _SKE fields that you see, they need to be unique, non-null, and this is the tricky part. They need to be stable across runs. So if you run the pipeline twice on the same input, the same customer needs to get the same surrogate key both for both times. So the brief suggests 2 approaches. Either you use a raw number with a deterministic order by on the natural key, or you can use hashing on the natural key with SHA-2 and then casting it to a big int. I didn't do that. I actually used an XX hash 64, which basically returns a big int by default, and it's very deterministic as well. So the hashing approach is generally safer for stability because it doesn't depend on raw ordering at all. Okay, so here's how I actually put stage 1 together. So on the left, you've got your 3 input files, your transactions, your account, and your customers, plus the config file feeding into the paths and the Spark settings. And then on the right, I've got the Docker runtime foundation. We've got the Docker file, the entry point script, and the few helper modules for explicit source schemas, for Delta setup, and the config for loading everything. So all 3 source files flow into the ingest.py file, which writes them out as bronze tables, raw data plus that ingestion timestamp, right? And then from bronze, everything flows into the transform.py file, producing the silver layer, typed, deduplicated, and linked. And then silver feeds into provision, which builds the gold dimensional model. You have got your dim accounts, your dim customers, and your spec transactions, all tied together with surrogate keys. And then finally at the bottom, we've got the stage 1 verification, a validation script, a trace script, and a notebook walkthrough. Okay, so now I'm building the Docker image by running docker build to package everything up. Instead of just running the whole pipeline end to end inside the container and only seeing the final output, I want to actually walk you through this cell by cell in a Jupyter notebook, which is running on Docker. So once the image is built, I'm going to open up Jupyter notebook that's bundled in, and then this lets me run each stage of the pipeline interactively and inspect the output as I go, rather than just trusting the black box run. Okay, so this is way more useful for a walkthrough, right? Because you get to see exactly what is happening in each step in bronze, silver, and gold, instead of just a pass or fail at the end. So I also tried to put in some comments to explain what is happening in each cell, to give you a bit of context of why we're doing it and what sort of implementation is actually being executed. That can actually help us to understand how each and every flow is actually running. So the first cell is all about setup, getting Spark Delta Lake ready to go inside the container. First, it imports everything we need. So we're talking about PySpark, your Delta libraries, Delta Lake libraries, YAML for config, the usual suspects. Then it sets a few environment variables to keep Spark happy inside the Docker. So pointing it to localhost so it doesn't run into network issues or hostname issues, which is common headache when running Spark inside containers if you've been running them like that. And then the next thing is it loads the pipeline config from the YAML file. So we're talking about driver memory, executor memory, parallelism, shuffle partitions, all externalized, so we are not hard coding any of this. It also stops any existing Spark session first, just to make sure that we get a clean session with Delta extensions properly applied, especially inside a notebook where you might be rerunning cells. Now, one thing is worth pointing out. So this notebook is actually running inside Docker container. So if you look in the Jupyter notebook, you won't see any data folder at all in the file browser. That's because that's not part of the image. So if I jump over the Docker desktop, check the bind mount of this container, you can see exactly where the local input and output folders are mapped to. So that's your data input and your data output inside the container. That's how the pipeline reads the source files and writes its output without any of that data living inside the image itself. So the next cell is about defining explicit schemas for the 3 source files instead of letting Spark take a guess. So why does this matter? By default, Spark can infer schema. It will scan the data and try to figure out types on its own, but that comes with a real cost. First, it's slow to infer a schema. So Spark has to do an extra pass of the data just to sample it and then guess the data types before it even starts the real work. So looking at 1,000,000 plus rows, that's wasted time and you don't ever get back. Second, it's unreliable. Notice that every time, even amount or credit limit or risk score comes in as a string at this stage. If you let Spark infer, depending on what values happen to be in the sample it scans, it might guess amount as a double in this current run, and then something else in another run. So that's not deterministic, and for a financial pipeline, that's very dangerous. The cell sets a handful of utility functions that get reused throughout the whole pipeline. So no point repeating this logic in bronze, silver, and gold separately. So a few key ones are the add ingestion timestamp, which basically stamps every record with what consistent ingestion time we talked about earlier on. And then writes and read delta simple wrappers for writing and reading delta tables using the override mode. And then inspection, which is the inspect table, gives you a row count, schema, sample rows, which is really handy for sanity checking your output as you go through the notebook. So now we are just reading the source files using the read delta function. So we start by reading the customer's bronze, and then we read the accounts, and then we read the transactions, as you can see. So we're also going to do like a display of the sample data. So we taking transaction bronze just to show how the data looks like. As you can see, we've got the sample data set, and we also have that ingestion time that we have added. And then after that, we're going to use the write delta function to basically write all the 3 files to the target output folders. So when we run the inspect table, it will basically give us a summary of the files that we've ingested. So I should expect to have the exact count that I saw on the brief, because we never changed the data set. We just added the timestamp. So the count should match exactly what we had from the input file with what we have in the bronze layer. So because I already ran this previously, I'm going to have some output files in the output directory. So I'm just going to clear that one out, and then I'll rerun the pipeline again, just so you see how the data gets populated from bronze, silver, and then the gold layer. So I'm just going to clean that up, and then I'll start over again. Okay, so now we are writing the output for the bronze customers table and the accounts and transactions. So we should be able to see the output in the target directory. There we go. So we've got the bronze and the customers. So I'm also going to run the accounts and the transaction, and then you can see that it actually populates in the target. Okay, that is done. So let's check again. So now we've got the accounts and the transaction table. So we've got our Delta paquet with the transaction log there. So we're good. Okay, this is the big one, the silver layer transformations. So this cell we've got, it actually reads the bronze tables that we persisted earlier on. That's your customers, your accounts, and your transactions straight off the Delta storage. And that's where the transform logic kicks in. So starting with customers, we basically dedupe. That's exactly one record per customer ID. And then we pass the date of birth into a proper date type. And then we cast the risk score from a string to an integer. So it's actually usable for analytics. So account goes through the similar process. We drop any records with the now account ID. Since that breaks our primary key, we dedupe and then we standardize the date fields and then cast credit limit and the current balance to a decimal data type for financial precision. And then finally, for transactions, we pull the province out of that nested location struct, and then we flatten it. We drop the nested location and metadata structs entirely to simplify storage. And then we dedupe on the transaction ID. We pass the dates, we cast the amount to decimal, we standardize currency, and then we add that DQ flag column, which will populate based on the quality rate. That's for stage 2. So the end result is we have got 3 clean, deduplicated, properly typed Delta tables, silver customers, accounts, and transactions written back to Delta storage, ready to be fed into the gold dimensional model. So before we get into the gold layer, I just want to quickly show you why I chose XX-64 as the choice for my surrogate keys, specifically because it's deterministic. So here I'm running a quick Spark SQL query, and then I'm going to hash on the names Tinashe and Tino. Notice each one produces a fixed number or a fixed numeric value. So if I run this again, or run it tomorrow, or even run it completely in a different session, Tinashe will always hash to the exact same number, same input, same output every single time. So that's the whole point. It's not based on row position or in session order, which can shift between pipeline runs, right? So it's purely a function of the value itself. So if a customer's customer ID hashes to a different surrogate key today, it will hash to the same surrogate key next week, next month, on a rerun anytime. So that stability is exactly what the gold layer needs for DIM customers and DIM accounts, and all the foreign key relationships between them. Now for the final piece, the gold layer dimensional model. This reads from our 3 silver tables and then builds a proper star schema for reporting. So starting with the DIM customers, we're going to generate a surrogate key using the deterministic hash we just saw. and then we calculate the age from the date of birth, and then bucket customers into age bands. Now, I'll be honest, the current approach is a bit basic. We don't want to be doing inline conditional logic, right? We need to actually have business logic separated into its own function or own implementation. So I think a cleaner way would be to define the edge bands as a separate lookup table, and then we do a broadcast join to pull those values in. The next is the dim accounts, which is the same idea. We generate the account surrogate key from the account ID, rename it to customer ref, rename customer ref to customer ID, so it aligns with the customer dimension plus the usual account attributes. Then the big one, which is the fact table. Here we join both accounts, customers and accounts, using the broadcast join, since both tables are much smaller than the transaction volume. So this is going to pull in the account S key and the customer S key as foreign keys. We also generate the transaction S key, combine date, time fields into a proper transaction timestamp. So all three tables gets written out to gold as dim customer, dim accounts, and fact transaction. So it gives us a clean star schema that's ready for reporting across customers, accounts, channels, and time, right? So now you have seen how each of these layers are implemented. So the actual transformation logic in ingest and transform and the provision is actually done. That's the one that is going to get scored, not the notebook. So I've already written all of that, and that's what I will commit to my GitHub.